For Unit 2, the big idea that we're going to be looking at is big idea number 1, which states that chemical elements are fundamental building materials of matter, and all matter can be understood in terms of arrangement of atoms. These atoms retain their identity in chemical reactions. And so the first thing that we're going to be looking at is section 2.1, the atomic theory of matter. And we're specifically going to be looking at how this concept of the atom has evolved over time. And the first that we're going to look at is Dalton's atomic theory. Now, there are 4 different main points for Dalton's atomic theory. The first is that each element is composed of extremely small particles, and those particles are called atoms. The second is that all atoms of a given element are identical, but the atoms of one element are different from the atoms of another element. So oxygen atoms are different from nitrogen atoms. And we know why now. We know about subatomic particles. We know what makes oxygen oxygen. We know what makes nitrogen nitrogen. During Dalton's time, however, not only could he not see these individual atoms, but he didn't know about subatomic particles. So this was revolutionary for his time. The third part of his atomic theory is that atoms of one element cannot be changed into atoms of a different element by chemical reactions. Meaning you can't create an atom from another atom. They can't be created, they cannot be destroyed. And this, another name for this, is the law of conservation of matter. Okay. For the fourth statement in his atomic theory, he stated that compounds are formed when atoms of more than one element combined. A given compound always has the same relative number and kind of atoms. So in this example, it shows nitrogen and oxygen combining together to produce nitrogen monoxide. There's one N and there's one O always in that compound. And this is the law of constant composition. The fact that H2O always has 2 hydrogens and 1 oxygen. So this is Dalton's atomic theory. Next came Thompson. Now, Thompson used cathode ray tubes, which are depicted right here in this diagram, and what he discovered was that cathode rays, which are radiation that originates from the negative electrode and travels to the positive electrode, what he discovered by placing a magnet on top, as you can see in B right here, the rays are deflected by the magnet, meaning they are no longer in a straight course, they're actually curved upwards. And what he discovered is that these cathode rays are actually a stream of negatively charged particles, and he called these particles electrons. So the issue here is that all of a sudden atoms are now divisible when before it was believed that they were the smallest particle that existed. Now we have subatomic particles, the first one being electrons, which are negatively charged and were discovered by Thomson. The other thing that Thomson came up with was the plum pudding model of the atom. And so what he said was that an atom is made up of mostly positive charge, as you can see in this diagram right here, the pink or the red. And what he said was that you have this atom which is mostly positive charge, and then there are some electrons interspersed in that atom. Now, this model, called the plum pudding model, seems really bizarre to us now, but it made perfect sense during Thomson's time. And so what happened was that Thomson's student, Rutherford, came along and tried to prove the plum pudding model correct. And so what he did, this is a revolutionary experiment, this is the gold foil experiment. What he did was he shot alpha particles into gold foil. The reason why he used gold foil was because you can cut gold foil extremely thin. And what he expected to happen was that the alpha particles would be deflected, because if most of an atom is positively charged, then alpha particles would bounce off the positive charge of the atom and bounce back and be deflected if most of an atom is positively charged. Instead, what he discovered was that most of the alpha particles pass straight through the foil, which made no sense at all. What that's telling us is that most of an atom is not actually positively charged. And he discovered that only a few were actually deflected, and they were deflected at extreme angles, angles that he had not expected. And so what this allowed Rutherford to do was come up with the nuclear model. And what the nuclear model states is that most of the mass of an atom is found in the nucleus. And the other concept that he came up with is the fact that most of the volume of an atom is not positive charge, it's actually just empty space. And then you have electrons moving around the nucleus. Section 2.3, we're going to be talking about the modern view of the atomic structure. So we've talked about Dalton, we talked about Thompson, we talked about Rutherford. Now let's actually talk about the atom now that we have an accurate view of what an atom actually looks like. So we know that protons, which were discovered by Rutherford, and neutrons, which were discovered by Chadwick, exist in the center of an atom. And electrons, which were discovered by Thompson, are along the outside of the atom. And you can see this here, this is the typical model. Now this is actually not correct, this is not a correct model of an atom, but for right now we're going to accept it because that's what we're comfortable with. Okay? Because atoms are so small, rather than using grams to represent their mass, we use the term atomic mass unit, the unit atomic mass unit. So 1 AMU is equal to 1.66 times 10 to the negative 24th grams. So it makes sense why we would need this unit, because an atom is so small that you would have to have very, very small values for mass if we used grams for the unit. The next concept is isotopes. An isotope is an atom that has the same number of protons, but it has a different number of neutrons. And the interesting thing is that isotopes have the same chemical properties, but very different physical properties. Okay? A couple of other important things. Mass number. The mass number of an atom is the number of protons plus the number of neutrons. The atomic number is just the number of protons. So if you look right here at this symbol, the number to the left in blue, the 12, that is your mass number. So that represents your number of protons and your number of neutrons. The 6 below represents the number of protons, and the chemical symbol is just what you would find on the periodic table. So this is carbon 12. Okay. For carbon, if you notice, it has a mass number of 12, but that's not the only isotope that exists for carbon. There's also carbon 13 and carbon 14. So if you look at the periodic table, you'll notice that the mass that's shown on the periodic table for carbon is not actually a whole number. It's a decimal. And what that value is that you see on the periodic table, that is actually the atomic weight of the atom. So for example, the atomic weight of carbon is 12.01. And so in this video right now, in this example, I'm going to show you how we calculate the atomic weight of an atom. In this example problem, it tells us that we have two naturally occurring isotopes of chlorine. We have chlorine 35 and chlorine 37. The atomic mass of chlorine 35 is 34.969, and its percent abundance is 75.78%. And for chlorine 37, its atomic mass is 36.966, and its percent abundance is 24.22. So to find the atomic weight of chlorine, what we're going to have to do is find a weighted average. Now, this is how your grades are computed in ARIES if your teacher has a weighted grade book. So what we do is we take the atomic mass, 34.969 AMU, and we multiply it by its percent abundance. Now, I can't just multiply by 75.78. I need to move this decimal place 2 places in order to make it a decimal, or divide by 100, so it would be 0.7578. And then I'm going to add to that the atomic mass of chlorine 37, which is 36.966 AMU, times its percent abundance, which is 0.2422. Now, we have to be careful because this is the first real calculation that we've done using significant figures. If you notice, the first step I do is multiplication of each of these, and then I need to add them together. So my final rounding is going to be based on decimal places, since my last step is adding. But I am also multiplying. So what I like to do is keep in mind, all right, whatever I get for this answer, it needs to have 4 significant figures because I'm multiplying. This answer also needs to have 4 significant figures. So I'm going to write out my work to show what it would be, but that's not actually what I'm going to be calculating. I'll explain as I go. So when I multiply these together,
I get 26.4995. So if I rounded to 4 sig figs, I would get 26.50 AMU. Now, I'm not going to use this value right here because I would have already rounded. And remember, I only want to round at the very end. The only reason why I put this value here is for you to know that when I'm adding, I can only have 2 decimal places, the 5 and the 0, 2 decimal places. For the next one, I'm going to take 36.966 and multiply it by 0.2422. I get 8.950501. So I'm going to round that to 4 sig figs, so 8.951 AMU. Now, what I've been doing in my calculator, I showed you my steps, but I just kept the 26.4995 in my calculator, and I kept the 8.950501 in my calculator, and I added them together, the unrounded values. And so what I end up getting for my final answer, since I want 2 decimal places from here, there are 3 here, so my final answer needs 2 decimal places, I would write it out as 35.45 AMU. Now, you might ask, why in the world would I need to put this if I don't even add these together? I add their unrounded values. And my answer to that is you don't need to write them. I actually never do. What I want you to keep in mind is the fact that you need 2 decimal places here, you need 3 here, so your final answer needs 2. If you can do this mentally knowing that this is 2 decimal places, you're good to go.